We tried to build a Turing machine to accept the language of A's, followed by B's, followed by C's. But the Turing machine we constructed would crash because once we eliminated the first A, B, C set, nothing would prevent the Turing machine from trying to read past the first square. We encountered a related problem with pushdown automata when we tried to reconcile acceptance by empty stack with acceptance by final state. In that case, we introduced a new symbol below the bottom of the stack. Well, let's do the same thing here. And notice that in our definition of a Turing machine, the tape alphabet could include more symbols than the language. This is one of the reasons why. So suppose that instead of deleting the first A, we replace it with a new symbol, X. We change the move from Q1A to QA print X and move right. This means once we return to where the initial A was, we'd read X. That tells us we should go no farther and should change the ready-to-work state. So if we're in our move left state, read X, we should change the state Q1, print X, and then move right. And so under our revised move, we know where the string begins, and we can cycle. However, there's a new problem. Eventually, we'll eliminate the last A, but the Turing machine doesn't know it's the last A. So it will move left until it reads X. It will then enter state Q1, reprint X, and move right. It's now in state Q1 and reading a blank, and if we don't define what happens when you're in state Q1 and read a blank, the Turing machine will crash, rejecting the string, even if it should enter the halt state. Now, we might define the move from Q1 if we read a blank to B entry into the halt state, but this would lead our Turing machine to accept strings like A, B, C, C, since we'd read the A, delete the B, delete the C, return to the start, and we read A blank while we're in state Q1, even though we have one more C. So if the last A has been consumed, we'll want to verify that there are no remaining B's or C's. So what if we defined our move from Q1 with the blank to move right? So the tape head would keep moving to the right. As long as we don't define a move from Q1 if we read B or C, the Turing machine will crash if there are any B's or C's left, which is what we wanted to do. So this should work. Or will it? Remember, if all the B's and C's have been removed, the tape is blank. But the tape is also infinite. So this move will be repeated indefinitely, and our Turing machine will never reach a halt state. Nor will it crash. So how can we solve this problem? So remember, reduce, reuse, recycle. We use the symbol X to mark the start of the string. We can use the same symbol to mark the end of the string. Now, this does mean we'll introduce some moves and some states that will take us to the end of the string and append an X. We'll let you figure out what those moves are. Now, when we read the last A, we're back at the beginning. We'll use our moves to read to the end of the string, and if we have in fact eliminated all the A's, B's, and C's, the next non-blank symbol we read is X, and so we define one final move where what we print and how we move are irrelevant since this is the halt state. And so now our Turing machine accepts strings of the form AN, BN, CN. But will it reject strings that are not of that form? Remember, you should be your own worst critic. So the moves of our Turing machine are, since the number of A's, B's, and C's are supposed to be equal, let's suppose they're not. First, suppose there are as many B's as A's, but there are more C's. Then eventually all the A's and B's will be eliminated, but there will be some C's left. So we might start with a string like this, and eventually derive a configuration like this. Since delta Q1C is undefined, the Turing machine will crash, as it's supposed to. The same thing is going to happen if there are more B's, since we'll eventually arrive at a configuration like this, and again, delta Q1B is undefined. What if there are fewer B's than A's? Then at some point, we'll have eliminated all the B's but still have A's. And that means we're going to go to the end and read a C, but since delta QAC is undefined, we'll crash. And again, a similar thing is going to happen if there are fewer C's, since delta QBX is undefined. What if we encounter an A, B, or C that's out of place? For example, this string has 3 A's, 3 B's, and 3 C's, but they're not grouped. In that case, we'll delete the first A and then go looking for the first B, but after we've deleted it, we'll run into an A, and delta QBA is undefined, so we'll crash. And a similar thing will happen if we have a misplaced B or C. There's one last case we should consider. What if we have no A's at all? So again, our Turing machine will begin. It'll be in the ready-to-work state, and it'll read a B which it doesn't expect. It doesn't know how to handle anything other than an A or a blank. And since delta Q1B is undefined, the Turing machine will crash, so this string would also be rejected. So remember, this is not a context-free language, so there's no pushdown automaton that will accept it. But we were able to construct a Turing machine that accepts this language, so Turing machines are more powerful than pushdown automata. Are they powerful enough?